Welcome to the 2026 Computer Science project, which is on forests. So I'm going to take you through the coursework overview of what you need to do for your project. I'll cover some ideas about what you could do it on. And the idea here is that I'm just going to give you like a buffet of cool things you could do. This is not going to be a how to do the project. There is no one way. The idea is for everyone to do it their own way and have fun and learn things along the way. So, right, let's break it down into the requirements of what you actually need to do. Hang on, let me give you some space. Right, requirements. 45 minutes looking for that microphone and it fell into my bag. Basic requirement number one, you need to have two inputs, meaning like a sound sensor if you're using microbit V2, or a light sensor, or a internal microbit, like a temperature sensor. That's just using a temperature block in makecode.org. Like that's not too hard. Can you use two internal sensors on the microbit without an external one? Maybe is the answer. I would, to be safe, try and use a breakout board with at least one external sensor, like with the little wires. But I would say maybe more than likely they probably will accept the two internal ones, but I'm just erring the side of like, you know, just very slightly overdoing it to make sure I'm not taking any chances, right? So you could get into a great debate about what is digital, what is not. So I'm going to move on to basic requirement number two. Basic requirement number two is to take that data down a USB cable from the microbit and onto Thonny and save it as a CSV file on your computer or your laptop or whatever. Now, I'm just giving one way of doing it. So yeah, you could use the data logger on your microbit probably to tick that box. I'm just talking about one way of doing it using Thonny. It's probably the most common way because you want an automated system and you want to use that data later, right? So I think that's probably the way most people, I imagine, would do it. Basic requirement number three. Basic requirement number three means you have to simulate something. So today it's kind of cold. I might get a hairdryer and I might point to the microbit. I might use a cold setting to simulate a cold wind. And I might get like a branch or something like that, you know, like this, and put my microbit onto the end of it with a bit of sellotape or whatever. Here I'm simulating wind. This shaking is simulating wind, right? If you have a hairdryer that's hot and cold, if you want to simulate light, put your phone light on it, you know, bright day, dark day, put books in the way for obstacles. All right, so that's what they mean by simulating. You want to have, I guess, in my examples I'm going to use is like different categories of wind. So I might do like a little Beaufort scale, you know. I won't do like force 12 hurricane and, you know, force 8 strong or gale and that kind of thing. I'll just kind of do pretty windy, extremely windy, you know, a few like if the value is between this and this, I say very windy. If the values, and that's all a simulation is. It's no more complicated than that. You can, if you want, go down the road of doing like modeling fire using little agents or simulating using random numbers on a curve. All totally acceptable. I'm just mentioning the easier way to do it first. So that's basic requirement 3. So advanced requirement 1 is to make a model. Now when I say model, they don't mean a predictable or testable model. It doesn't say that anywhere. You just have to practice making your own like little kind of maths equation. For example, you know, happiness is love times free time divided by dread. That's a silly pop science model, right? Now, technically that is a model, and as long as you write down something like ignition risk, what's the chance of this forest going on fire? Probably low, but I bet you it's got something to do with temperature. So I'm gonna say it's temperature times, you know, like maybe the light, because there's a lot of light coming through here, therefore there's probably some stuff in the ground. It doesn't have to be super accurate. Yeah, temperature times light, you know? And if I get a crazy number like 0.0001, I might multiply it by 10,000 to bring it back up to, so that my answers are somewhere between 1 and 10. I can do it. It's my model and you can't stop me, you know? And actually when you look into maths later on, you realize things like the UV index, that's kind of how it works. It is literally like, do you ever wonder how the UV index tends to be like between this number and that number? They just normalizes, and it's heuristics, right? It works good enough, you know? You don't get sunburned if you look at this index. It's not super like, the universe never invented a UV index at the beginning of the big bang. It's just a thing humans made of, and you can make up your own one too. It's easy. Speaking of models, AR2, you have to come up with 2 things for your advanced requirements, 2 what ifs. So let's use our example of ignition. We said like ignition is temperature times light, right? I will say, well, let's test this model, right? If I set my light, if I hard code my light to like be very bright, so I look at my light sensor and I say I take the highest, brightest value with my torch, and then I take the temperature to be something pretty high. I guess like 40 degrees is a very, very hot day in Greece. And I multiply those 2 together using my equation in Thonny, and I say, oh yeah, that does give me a pretty high ignition risk. So there's what if situation 1. And then scenario B, or situation 2, whatever you want to call it, I might set them both to low and see, does my ignition risk go down? Is it sensible? Like, you know, that way I could test it out. And that's all you're doing. You're just coming up, you're looking at your model from AR1, and you're just subbing in these 2 values, what do I get? Sub in these 2 values, what do I get? What if I put 1 high and 1 low? Yeah, what if I do like really high temperature but really low light? That's the point. You're testing your model using what ifs, all right? So you're subbing 2 values into the your model that you made, and you're kind of saying, does that make sense? All right. And finally, number 3, there's a few different things you could do here. Probably the easiest is a threshold trigger. So like, if my ignition risk, as I said, gets really high, I might like sound a little buzzer on my microbit, or I might have like a little servo, you know, one of these little arms that I can have going from 0 to like 11. Extreme risk, you know. Or if I'm looking at moisture, I might like tip over a little glass of water that would water the plant, you know. Any physical response to a measurement. And it also doesn't have to technically be your model. It says in the brief that it can be like just a sensor, because I think the example I gave was, yeah, if the soil moisture is low, add some water to it. So that could just mean that if your temperature is a certain thing on your microbit, sound some alarm, do something physical, have something pop up, okay? So let's look at a few sensors you could use for your project here. I've got a microbit, a breakout board. I've just got it powered up to a USB bank at the moment, but you can get little battery packs, or just leave it plugged into your computer. You don't need that sort of thing. And I've got here my favorite sensor, which is a light sensor. These light sensors are great because you can put your finger over the top of them, so like that, to simulate different types of lights. And it's so much faster than messing around with like temperature. You can't change the temperature, humidity very fast. So if you see that little snake kind of pattern, that's the light dependent diode. And this guy is an external sensor, and you can see there it says on it very clearly like AO for analog output. Don't plug this into the digital one. I suppose you could tick off your digital output if you wanted to, you know. But I mean, I think that undeniably satisfies analog, because it literally has A for analog on it, right? So yeah. But as I said before, you might get away with just using the internal ones, because they might decide it's, you know, unfair to people who don't have that equipment, which is kind of fair enough. So I'm just covering myself. So I've got this guy here plugged in to pin 2 on my microbit, and I'll go through in the basic requirements 1 how to code and wire these sensors up. Right, I'll just show you a few of the sensors while I'm here. I've got a soil moisture sensor. You could use that if you wanted to. Okay, very same, it just connects up. Well, actually all sensors connect up with 3 pins. I'll go through that video. We've got also this is a soil temperature probe. So you put this into the soil. Got one of those, and another favorite of mine, these DHT sensors, this digital humidity temperature sensors. They'll read both temperature and humidity much better than the internal microbit sensor, because like that always tends to be like 20 degrees, because you know this thing generates its own heat by being plugged in and near a computer, so it's never very accurate. Whereas if I want to, and I do, measure the temperature around my house, like for like Home Assistant and things like that, so I'd use a few Raspberry Pi Picos, these little guys, these little guys here, Raspberry Pi Picos, and these to monitor the sensors or the temperature around my house. And you can use this also for your project. It's the very same as like a microbit, except it's got the pins, so it doesn't need the breakout board. It's got MicroPython on it. So I might do a video on how to use that for your project as well. But that's pretty much it. I think most people are going to be using this little guy. You can, if you want, to use like a plant for decoration, you know, and put your capacitive, your soil moisture thing. I would just say, if you are getting a soil moisture sensor, you don't have to. I'm just saying, if you really want to go mad and spend a lot of time, probably unnecessarily at the start of your project, trying to get the first sensor to work, make sure you get the capacitive versions of these. Don't get the conductive ones, because the metal plates immediately degrades on contact with water. One would think that something designed to go in water would be waterproof, and one would be wrong, because it's €4 on Amazon. Where these ones are slightly better, but even that, they measure moisture and not like soil, like water level. So it takes a little bit of fiddling around with, and you might get some unexpected results, right? But you should be aiming to do this all in the lab and not wandering around a forest. I mean, that'd be cool if you got a forest nearby. You certainly can, but you don't be putting yourself under pressure. You can simulate all these things just by simulate light, by moving things in front of the sensor. You can, this is microbit V2, right? So it's got a sound sensor, so you could do that, for example. If you had 2 microbits, you could get the radio signal strength in between them and then pass objects between them if you wanted to, like, measure the, I guess, kind of the thickness of something if you wanted to. And of course, you've got the acceleration for putting this onto a branch and shaking around to show wind. And there's the compass as well. If you want to put it on, it'll like a weather vane, and it'll show you the degrees of the wind, like what angle wind is coming from. Cool. So that is it for the overview. And I'll just do one example now of a project code. The example I'm going to do is this guy here, which is going to be the internal temperature and the external light level from this guy. Right, so here's my program. I've broken down the basic requirements here and the advanced requirements. Now in this one, I'm not going to go through all the code. I'm going to do that in individual videos for the basics. I'll just show you how this works. So firstly, I've got this set to my microbit on COM11 here. So you can see this is streaming in. If I just stop it and start it, you actually can't stop it because this is just continuous stream coming through. So what have I got here? I've got a temperature, a light, and all that kind of stuff. Now I'm going to go back into my program. My program hasn't started running yet. Right, that's just checking the stream is coming in all right. And I'm going to press go on it. Right, so you can see here I've got my temperature, which is 19. My light, which, let me just move it around because it was stuck on 1023. But actually, that is, if you ever see that number, that means it's maxed out, right? I might just play it again here and just move it around. Oh, there we go. You can kind of see you get more interesting data there if I move it towards the light. Okay, so let's explain what's coming out here and how it ticks all the boxes for all the requirements. So on the microbit, I'm sending my serial and my temperature there. You could see that when I clicked microbit, it was coming in from the sensors. And that is all done in microbit block coding. Then when it gets to Thonny, I'm going to save it using a CSV. So I'm saving that to a CSV file.
and that ticks basic requirement 2. The canopy thickness simulation is what I chose to do in this particular example. So it's just I showed it before, but it's an if else that just says if the light is between this and this, it's that canopy thickness, right? You don't need to necessarily send this to Thonny, but I kind of just want to keep an eye on it and make sure it's all working. So it's handy so I don't have to keep going back and forth. Advanced requirement 1 here. I made my ignition risk model. So in this case, I found that it gives sensible readings when you get the internal temperature and you divide it by the external light sensor value. Now, how did I get to that? I'll explain more in that video how you would work out. It's some very, very basics algebra of what goes above the equation, these kind of uppy relationships, and what goes below the equation, like inversely proportional. As one goes up, the other goes down. Okay, so as long as they're at a reasonably sensible place and like the ignition risk is going up, the hotter things get, right? I think that you'd expect your model to do at least that. You'll notice also that I've got times 1,000 minus 19. Where do these numbers come from? Well, you can see that my AR1 risk here, when it computes it, they are fairly reasonable numbers. Like they're not 0.0099 blah 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 blah. So that's because I took the raw output when I just divided the two, and it wasn't giving me a nice number. So I normalized it by bumping it up by 3 decimal places, and then I found it was slightly high. It would never really go down to 0. So I subtracted 19 until sometimes it hit 0, you know. And that's a very crude way to normalize. There's actually a formula for normalizing things. And I'll just finally say that you absolutely do not need, it doesn't say anywhere in the requirements that you have to normalize. By normalize, I mean take readings from your ignition risk, what you've calculated, which are very ugly numbers like 0.00 or 1,009,000, and turn it down to a nice like 1 to 50 scale or 1 to 10, you know, as in like, because, you know, the UV index would not be popular if there was 95 decimal places in it. No one would use it because, yeah, it just wouldn't work. Cool. So that's, again, I'll explain exactly how to do a few different of these in that video. The what ifs, you can see here, I put this at my bottom of my program afterwards. So in scenario A, I've got a thin canopy, high temperature. Okay, so that would mean very high light levels and very high temperatures. So I said it's going to be 35 degrees. This 300, when you play around, you'll find that the light sensors are inverted, right? So the lower they go, the actual brighter they are. That's how inputs often work on microcontrollers. So your options there are to just remember that that's a thing, or I suppose you could invert it with some software. But I think it's just the less things, the better. So my model result is when I put this in, I got a 98 when I put it into this equation. Okay, and these I've hard coded in this. Now, hard coding is normally a bad word, right? But in this case, well, of course, you're investigating with a scenario, right? So, and then I also added on this little extra thing. This was optional. I don't think you have to do this, but I just thought a good way to test your model would be if, like, I put in high values for both and I'm expecting a high ignition risk, as you would be, very high temperature, very high light. Like, does that give a high number? So I put in a very little if-else statement saying, if the number is above, I think I have it like 50, you know, ignition risk is high. Yes, the model works. If it's below 50, well, I'm not getting what I should be getting from this model. So this would have output, redo the model. It's not working right now. You know, more temperature should not have a lower ignition risk. Your model is busted. And then I did the same again with thick canopy, low temperature. So I set both to low. And again, I've got here 4 is what came out of it. Okay, when I set the temperature to 14 degrees and the sensor is actually darker there at 600. Remember, I'm saying it's like this is actually darker than 300 because the inputs on light sensors are in reverse. So the bigger the number, the darker it is. And I didn't originally get 4. That you might be like, wow, that is not a nice thing to get. Yeah, this is where this came from. You know, I had to fiddle with it and play around with it until I had it reading nice, happy fairy tale numbers that I liked. Again, not necessary for the coursework, but maybe necessary for, for your pride. Okay. And finally, AOR3. You can see for AOR3, a high ignition risk alert came along here at this point. There are date and time stamped actually in the CSV. I didn't put that column in, but yeah. So there's an alert. Now, I'm not sure if that's just quite enough to say like just a very quick, if thing is above this level, print a line. So because it was like 3 lines of code. So I went a little bit beyond there. They did say it has to be adaptive. So that might be something that I suppose they could argue that it has to be something a little bit more complex, or like more than 2 lines of code. So I, for example, here added a trigger. So my threshold is here. This is for my alert. But I added a little flag. A flag is how you know something is already going on. So this is a Boolean data type. It's like 1 or 0, on or off, high or low, right? So the alert flag is set to false at the start, which means there's no alert playing. And the function here is like, you don't want your alert playing over an alert, playing over an alert. Imagine that. That wouldn't be fun. So I say, hey, before you send the alert, will you just check that this is not true? Because if it's already true, chill. Like don't be doing like 10 more alerts, So it checks if it's playing first before doing that. So that, because it's checking it's going back and checking the state of the system, like it's adapting to what the system is doing. So I would say that arguably is adaptive. That's my interpretation of it. Might be totally fine just having a simple 3-line trigger, but I'm just trying to do slightly more and read in between the lines and make sure I'm fully covered in everything I do here. I'd say as well, like, I've done this because I can show students like an example of this in Thonny, and it's all nice and neat in Thonny. Now, I would recommend just doing AOR3 probably on the actual microbit itself, because it'd be way easier to just say if the temperature is above 50, like sound a buzzer or move a servo or something like that. You don't necessarily have to report it back to Thonny, but I said I just want to keep everything as much as I can in one place to show my work here. So that's it. That's basic requirements. That's my advanced requirements, and that is all for this example. So that's the coursework overview video. I'll be putting on Patreon an updated version of my guide. I'll be updating that from last year, which is like a comprehensive guide of how to do each part of the report, like where the common mistakes are, why people lose marks, where the most marks are to be gained, and with like examples and that kind of thing. So just be sure though that you read the brief yourself. It is your responsibility to read the brief. It is the responsibility of every student. If you take advice or templates or examples from teachers, they may be out of date. They may come from previous years, and it does change. The marking scheme changes every year. So it's up to you to read the brief and to do your own project, and not be assuming that the resources you're getting are up to date or accurate. So in the next few days, I'll be doing a basic requirement 1 video first, which is going through the code for how to do that, and then basic requirement 2, and on and on and on. I might put up maybe tomorrow some ideas of topics you could do. Like, do you want to do like wind disasters? Because this has to be in relation to forest disasters. So that might take some thinking about like, okay, I have my sensors, but like, how could I turn this into a project? Like drought, as I said, ignition risk from this video. So things like that. So yeah, keep an eye out on YouTube's for the next few weeks. I'll be cranking out videos and looking forward to it.